Okay, welcome again to this webinar on reproducibility in science. This is a webinar which is organized by Ghent Core. I'm Stephanie, I'm part of the Open Science team at Ghent University and part of Ghent Core, the community for open and reproducible research at Ghent University. And today we have two guest speakers, Denis and Thomas, who are joining us to introduce us to the reproducibility crisis in science. And with that, I move to the introduction of our two guest speakers, Denis and Thomas. Denis and Thomas are directors of research at INRAE in France, and they both have a background in evolutionary biology and ecology. And for almost 10 years now, they are part of Peer Community In. They co-founded Peer Community In and are now member of the PCI board. PCI is an initiative to improve scientific publishing outside of the traditional systems and journals. And they aim to provide a process which is both free for authors as well as for readers. It's heavily relying on communities of researchers to participate in the peer review process, such that the evaluation and recommendation of preprints happens by people from within the field and are ready for publication both in a peer community journal or in other journals. So as such, PCI promotes high quality and openly accessible research, and that's of course a topic which is very important to the Ghent Core community. So today, Thomas and Denis will share their view on reproducibility and science, and I'll give the word to Thomas, who will start with his presentation.
So again, thank you very much. It's very intimidating to speak about reproducibility crisis in front of such a group. So we hope that we are not going to say things that are too simple and too silly. So we are interested in the problem of reproducibility because we are researchers, as it was said during the introduction, and because we are also editors, and we try to transform a bit the way articles are published in the current system. So, a part of the slides that I'm going to show you, that we are going to show you, are inspired by a colleague of us who is responsible for Peer Community in Registered Report, who is Chris Chambers, and he made some very nice slides about reproducibility issues and PCI registered report. So some of the slides are his slides. So just to introduce you the problem that you probably already know, but let's do this introduction again. This is the cycle of the ideas in science. Okay, so we first try to generate and specify hypotheses, then we design studies to, for instance, test the hypothesis we made, we collect data, then we analyze the data and we test the hypothesis with statistical framework, we interpret the data, and then we publish our ideas and we conduct the next experiment if necessary. And in all these steps, there might be some problem that come from the fact that researchers are under pressure to get more and to get great results. So the problems could be the fact that we have a lack of replication, that's during the design of study that we have very low statistical power because the study are under dimensioned. There are problems of selective reporting between the collection and of data and the analysis of data, problems of selective reporting, and problems of hunting significant p-values during statistical tests, which is called the p-hacking. There are some data dredging during the selective reporting, and also a very important problem, which is the hacking, when you set the hypothesis after the results are known, so that there is a change in the hypothesis between the beginning, where we specify the hypothesis, and the end of the process, where we interpret the data. And one of the main consequences of all this is that there is a huge publication bias in the literature, with most of the results being positive results. And I'm going to talk more precisely about that in a few slides. So we are going to focus and to concentrate on these two problems, which are the publication bias and the very low statistical power, because we think with Denis that they are the main problems in the current scientific ecosystem. So just a few slides about the problem of the publication bias. So the fact that most published results are positive results. So this is a very famous study by Fadeli, published in 2010. And you have here the percentage of papers that report a support for the tested hypothesis. And it is between 50% here at the minimum and 100% here. So you see that most of the publication in the various fields of science, in the various fields, show positive results, with some extreme results like 90% of the papers, for instance, in psychology. You also have other studies showing meta-analysis results that show the same. For instance, here we have the percentage of null findings that are reported about 10%. And in this study by Schill and collaborators, showing a percentage of positive results of about 95% in their study published in 2021. And it is true also, for instance, in medical trials, where, for instance, in this study, 94% of the trials that were analyzed were concluded positively about the results. And we can add many, many more articles about that. So this is a very stable results. Most of the results are positive, which is a bit surprising. So what could be the situation in which your results could be positive and significant? So you need that the effect size are real. This is the first thing. You need also that the variability of the phenomena or the measurement of the phenomena should not be too large, because it would hide the effect size. And also you need some large sample size to be able to detect the effects and to be able to have enough power to show statistically that you have an effect. And so this leads to the definition of what we call the power in statistics. So you know what it is, but we can remind it. Basically, the power is the probability that you will get a significant effect when there is indeed an effect. Or it is the capacity, our capacity to detect real effects, or it is the fact that we can detect true effect or true positives. And here with these two distribution, with the distribution of, let's say, the null hypothesis and the distribution of your samples, you are able to detect a significant difference between the two distributions in this green area here. And this represents the power, which is 1 minus the type 2 errors in the test. And also you have in brown here alpha, which is the type 1 error. So, and the largest the green area is, the more probable you will be able to show that there is a difference between your, let's say, treatment effect and the null hypothesis. So for instance, with these three graphs on the right here, you have a power of 100%. So it means that whatever your measure is in this distribution, it will be significantly different from the null distribution. And of course, here you have a much larger size effect than here, where you have a smaller size effect that leads to a smaller power. So the larger the size effect, the bigger the power, the larger the probability you have to find a significant result. So if we look at the distribution of the power in the literature, so if we read the articles and we just look at what is the power of the statistical analysis that were made in the studies, we can have an idea of whether the results were obtained in good conditions with a large power. So, for instance, in this paper of 2003 in behavioral ecology, Jenians and Moller showed that, in approximately 700 papers, the average statistical power was about 13 to 16% to detect small effects and about 40% to detect a medium effect, which is very, very low. In this study in ecology and evolutionary biology, Young and collaborators showed that the statistical power was in average of 15% with a problem of overestimation of the effect that were measured. In neuroscience, we also have this kind of meta-analysis results with Button et al., who showed in 2013 that the statistical power of the studies was approximately and in average 8% across almost 500 studies. And so this is it was in neuroimaging, and in animal models among 19 studies, the power was between 18% for medium effect to 31% for medium effect. So in any case, the power was super low. And this is for trials in medicine, in clinical trials. You have this nice graph showing you the distribution of the power through time with the tendency through time of the median of the power. So it's between 1975 and 2015. And you can see that the median of the power is about 10% in all the clinical trials that were recorded here. And you also have other statistics. So, for instance, the proportion of studies with a power larger than 80%, which is like a standard to make good studies and good comparison. This percentage was between 5% and 9% in 2015. So again, some very, very low percentage of papers playing with large power and with powers that are standard and that are considered okay to make analysis. And here you have distribution with a very huge mode of less than 5% of the articles as a function of the power. So you can see that the frequency of the papers with large power is very, very, very small in this compilation. So we have a very strong paradox because most publications report positive results, like 90% of the publications, and most publications have a very low power and should not be able to report positive results because they have a low power. So they should not be able to report those positive results. So this paradox leads us to question the fact that the positive results that are in the literature are real positive, or if they are false positive. So we can ask this, are the positive results that we see in the literature false positive or real positives? So I'm showing you here a figure that you may already know, but it's just a way to make it clear that there is a relationship between the power on one side and on the other side the probability to get true positives among the positive results we have. Okay, so here in this figure, you can see in orange the situations, the cases where your hypothesis is false. Let's say the universe of your false hypothesis, and here in red, you have the universe of your true hypothesis. Here in black, you have the type 1 error. So let's say alpha, the 5% cases where you will detect a true effect when your hypothesis is indeed false. Okay, so let's say here you have these 5%, let's say 30 studies. And here in green, you have all the situations where you have a significant effect when indeed your hypothesis is true, okay? And this is the power. So this percentage here, let's say 30%, is your power, okay? And with a power of 30% and with let's say, I don't remember how many, 600 and 300, so there are 1,000 hypotheses here. So here you have 120 hypotheses that corresponds to the power that are detected as true when they are, if that they are indeed true. And here you have 30 hypotheses that are detected as true when they are false in reality. So if you take this number of hypotheses divided by all the hypotheses that appear true, that are shown in blue here, you have this ratio here, which is the ratio of the true positives over all the positives, including the false positive. And this is what we call the predictive posterior value, the predictive positive value, excuse me, which is the probability that your positives are true positives. And if we rewrite everything as a function of the power here in green and the type 1 error here in black or in dark green, then you can rewrite the formula and this leads to this ratio here, where the power is on the top and below the ratio. And this ratio is a positive and increasing function of the power. So it means that the less you have power, the less probability you have that your positives are true positives. And the bigger your power is, the larger is the probability that your positives are true positives. So if the power is null, for instance, this ratio is null. If the power is 100%, this ratio is about 95%. Okay. So it is the predictive positive value, the ratio of true positives over positives, is an increasing function of the power. And it is also an increasing function of your size effect. So here it is the odd ratio. So when the size effect is small, you have a low probability to have real positives. And the larger the positive effects are, the larger is the predictive positive value. And this was shown by some colleagues, Button et al., for instance, and they clearly stated that a study with a low statistical power has a reduced chance of detecting a true effect. This is the definition of the power, okay? But more importantly, the second part of the sentence is here, and this is important. It is less well appreciated that low power also reduces the likelihood that the statistically significant result reflects a true effect. And this is super important result. When you have a low power, you have a large chance to have false positive among your positives. And it was said also by Ioannidis in 2005, the very famous paper by Ioannidis, where he said that simulation shows that for most of the design and settings with low power, it is more likely for a research claim to be false than true because of this very, very low power. So the main consequence, and the second main consequence of a low power, is an increase of the probability that your positive results are indeed false and not positive. And it has a second consequence that I'm going to show you, but probably you already know that, but I just want to show you because I find it so nice. So if you have a low power here in dark blue, then, and here, this is the distribution of the size effect, okay? If you have a low power, you will be able to detect an effect only if you are in this area here. So it means that even if the true effect is about 0.5, then what you will be able to detect is something about larger than 0.6 up to an effect of 2. On the contrary, if you have a large effect, then you will be able to detect significantly an effect of 0.5 when it is indeed 0.5. So it means that when you have a low power, then when you get significant results, you have a very large chance to overestimate the effect you measure. And this is here a result of simulation. You have on the x-axis the statistical power, and you have in the y-axis the average reported size effect. So here the true effect is 0.5. So it is here, 0.5. And when you have a low power, of course, you detect a much more larger effect than 0.5. And again, the lower your power, the larger will be the overestimation. So this is the third very important consequence of the lower power that can lead to problem of reproducibility.
Thanks a lot, Thomas.
Yeah, so Denis, I am going to
I will share pointer.
Okay. Yeah.
So do you see my screen?
Yes.
Excellent. Thanks a lot, Thomas. So what? So as Thomas explained, most published studies report positive results, but at the same time, many of these studies suffer from low statistical power. This is a critical issue because low-powered studies are not reliable at detecting true effect. A large proportion of published findings are likely false positive. And even when effects are real, as said by Thomas, they are often overestimated. So to put it straight, many results in the literature are probably false. This concern is not new, and as early as the 1990s, several authors had already pointed out this issue, and over time, this led to what we now call the reproducibility crisis. So it's true in many disciplines. So with Thomas, we took a screenshot of many titles in many articles in many disciplines. So to get a sense on how widespread this concern is, last year we performed a search in the Web of Science using the following keywords. So you see many keywords. We have included, of course, reproducibility crisis, and with several crises like reproduction crisis, replication crisis, but many other keywords with the reproducibility issue. We found a total of, so we did this research from 1990 up to now, and we find more than 500, almost 5,000, and 400 articles published on the reproducibility issue, and almost 1,800 used the term crisis. But this issue is not equally distributed across discipline, and psychology is a field where reproducibility concern have been the most visible. So in this figure, the bar shows the proportion of reproducibility-related articles, so since 1990. The red bar concerns all the proportions of papers using the term crisis, and the green bar here corresponds to the proportion of articles using other keywords of the reproducibility-related term. So actually, it's not very surprising that it's in psychology that it is the most important. We will see why, but it's not surprising. Like in physics and mathematics, there is no so much reproducibility crisis because there is not a lot of variability and not a lot of empirical studies in those fields. But in biology, for example, or in ecology, in agronomy, we can expect a lot of variation, a lot of empirical studies, and a lot of crises, a lot of false positive, actually. So we can zoom on psychology, and we see something very interesting. Researchers in this field became strongly aware about the problem about, let's say, 10 years ago, and began explicitly referring to it as crisis. You see that most articles are in red, so using the term crisis when talking about the reproducibility issue. But now look at the medicine. So it doesn't start like 10 years ago. It started long before, like already in the 1990s, you can see articles related to the reproducibility crisis, but they didn't use at the beginning the term crisis. They used several other words, but they started to use the term crisis like in psychology in 2015, and then you can see an increase number and increased proportion of articles using this term of reproducibility crisis or reproduction crisis or whatever. So the key question is then, do we have really a reproducibility crisis? And the answer is clearly yes. There are systematic reproductions of experiments in life sciences, and they show that the success of reproduction of those studies are less than 50%. Look at this one. On 67 cancer studies replication, there were only a 20 to 25% that were coherent with the original results. You can see another study on 53 articles, and the results were only confirmed in 6% of the cases. And similar in this study, 15 experiments out of 100, almost 200 studies were reproducible. And there was also try to replicate studies published in Nature Genetics, and over 18 articles there were a reproducibility of only 2 of them, actually. So this is also what they've found in preclinical trials. So this is different studies that tried to replicate preclinical trials. And you can see that in this study, so this is not reproducibility. Look at its prevalence of irreproducibility. So in that case, it was 89%, or it was less than 10% that were reproduced. And you can see different studies, and there is a mean of irreproducibility of almost 58%. So it means that most preclinical trials are not reproducible. So an important point, as said by Thomas, is the number of sample size. So the sample size justification. It's really important to justify the sample size to explain how powerful your study is. And what we can have a look at is in scientific journals, if there is something about requirements of sample size justification in authors' guidelines. So with Thomas, as said by Stephanie at the beginning, we are evolutionary biologists working on insect pests. So we had a look on a few number of journals in evolution, in ecology, and in agronomy. And interestingly, in those journals, like in Evolution, Ecology Letters, Journal of Evolutionary Biology, New Phytologist, there is nothing in the guidelines of those journals for a requirement about sample size. In some journals, look, for example, Ecology, they only say power analysis occasionally can be useful. So it's not a requirement, it's just a suggestion. If you look on the PLOS journals, they only say, if appropriate, provide sample size. So it's, again, not a requirement. Just as PCI, so Stephanie said, we started PCI, and at PCI, because we consider this as really important, we ask for a clear justification of sample size for all empirical studies. So with Thomas, what we wanted to do is to have a better idea on the different disciplines, in 4 different disciplines, in medicine, in psychology, in ecology, and agronomy. We wanted to see the frequency of requests to justify sample sizes in authors' guidelines. So it's a pilot study that we did for a stage 1 registered report. It has recently been accepted. In those 4 fields, we randomly selected 20 journals to make an estimation of the proportion of journals requesting to justify sample sizes. And we have found big differences with medicine, with 65% of those 20 journals requiring to justify sample sizes, 40% for psychology, and only 10% for ecology and agronomy. So it suggests a high variation with the lowest levels of requirements in ecology and agronomy. So we will start the stage 2 registered report. So the full study for this, it's in progress. We will do this in the next few weeks. So where do we need to go? We with TOMA, we think that we must try to scientifically justify our sample sizes. We must choose the right methods and for hypothesis testing, for exploration. Hypothesis testing must have a high level of power analysis based on literature or preliminary data with taking into account the effect size, the variance. And so we must educate the scientific community not only on scientific knowledge, but also on scientific methods. So one way to improve the situation will be to make research quality to be determined solely on scientific validity, question and methods, and never on the results that studies produce. And we know that there is a push for researchers to have positive results because it's easier to publish and easier to publish in prestigious journals. So one way to have those research based only on the scientific validity is the use of registered reports. We know that most of you are familiar with the registered reports. It has been created by Chris Chambers at the beginning of 2013. It was an editorial in the scientific journal Cortex. And the central aspect of the registered reports is that researchers decide hypotheses, study procedures, and main analysis before data collection. And those are peer-reviewed before studies are conducted. And if there is a validation of this protocol, there is a kind of in-principle acceptance of the stage one. So, and then the stage two. So there is a virtually guaranteed publication. So how registered report works. There is a stage one of registered reports with the context, with the questions and hypotheses, and methodology. So this stage one is peer review, and if accepted, there is an in-principle acceptance. In case of in-principle acceptance, the authors can realize their experiment or field work and make their analysis, and they can submit to stage two, which is a complete article with the context, question, hypothesis, methodology, and of course the results and the discussion. And the stage two will be published as a final article. So what is really interesting with registered reports is that none of these things matter. So there is no question of whether the hypothesis is supported or not supported, whether the p-value is below 0.05, whether the results are novel or not, and whether the results have an impact. That's really important. So our registered reports working as intended. You can see at the beginning of the talk, Thomas talked about the traditional, the article published in traditional literature with a percentage of null finding around 12%. If you look at the null findings in registered reports, they are much higher, around like 60%. So the hypothesis is almost 5 times more likely to be unsupported by registered reports compared to regular articles. So Thomas also showed you this standard for the standard report, the percentage of paper with that validates the hypothesis, which is above 90%. If you take registered reports, it's like more around 42%. So 10 years later, what we can say is that registered reports is now mainstream with more than 350 journals and with more than with 1,000 registered reports published. So registered reports can be submitted in many generalist journals and in biology, neuroscience, linguistics, now chemistry, physics, and now in many, many journals. As you probably know, but if not, we have a specialized peer community in registered report that has been started by Chris Chambers and with some other colleagues. There are some characteristics. There are free for authors and readers, like all PCIs preprints recommended by PCI. It's non-commercial. There is an evaluation of registered report in all disciplines, so it's kind of pipeline for all registered reports. Recommendation and evaluations are published, or if accepted, and publication in peer community journal and other journals, as said by Stephanie at the beginning, can be done, including 40 PCI registered report-friendly journals that accept stage 2 registered report recommended by PCI registered report without additional reviews. So where are we from? So they started in 2021, so they have now almost 190 recommenders, which are associate editors. They have received more than 600 submissions of stage 1, more than 200 submissions of stage 2, a lot of reviews, recommended more than 300 stage 1 and almost 150 recommendations of stage 2. That's it. Thanks a lot for listening, and with Thomas we can answer all your questions.